In this project, we will demonstrate process improvement simulation. So this process is for excavation, and we have two parts participating in this process is planning and operations. And here we see this excavation process is used as a part for the analysis. So we expanded analysis into separate block in order to not affect the excavation. Also here we see a couple of requirements. We constrained production, produced and wasted. We see that produced shall be more than 3 million tons a year, and wasted shall be less than 10,000 tons a year. So we track wasted material and produced material. We have also excavation rate, 100 tons per day. And now next step is actually to model the excavation process. So in this case, this excavation process is modeled in the sequence diagram. So here we see planning and operations. And here we see current schedule. We start operation on the current schedule. We do production. And on the random time, duration conformance to plan, we dig in the right place. Then some errors in the plan happens and we start digging in the wrong place. So duration deviation, this is random again, where we dig wasted material. So here we see this wasted. Then we request to update the plan, and the plan is updated. And then we again start digging on the right location. So again, production is valid. Now we simulate this in 2 months period. So we have the rest of the time correct, and up to the 2 months period, we simulate this single flow. So we see here random, see random here, and then the last one is actually just whatever time left till end of 2 months period. Now, if we want to simulate it in the year period, and let's say that we need to repeat this cycle, so we can put it into another cycle, and then that we can do, for example, with the activity diagram. So here we see, let's come back to this analysis, and here we have activity diagram, which is actually, you see, introduce this iteration property decrease. It calls also excavation sequence diagram, and then iterates back. There are two more opaque action elements here, which are also used here to randomize the values for the duration conformance to plan and duration deviation. So we see that conformance to plan is from 0 to 7, and duration deviation is from 0 to 30. So up to 30 days, we can deviate kind of a lot. Those numbers can be changed here. They can be also produced as the variables. And here we see also next analysis piece is that we do the total per year. So every time you do one cycle, so the total is increased by that cycle duration conformance to plan and duration deviation. That at the end, we would have duration conformance to plan per year, duration deviation per year also. So we see those properties here. They are the value properties for excavation. Now, why do we have here two choices, excavation as this, excavation to be? This is because we wanted that demonstrate the difference between this process and to be. So in this process, we see that duration deviation is actually from 0 to 30. In this to be, we can put another behavior, and in this case, duration deviation is always 1 day. Could be more randomized, and just that is the initial analysis what we want to perform and compare. So we could execute this, then we could pick excavation as this or excavation to be, and then run through that sequence diagram through the whole cycle of the year. Now, additional complexity here is that we want to imitate that there are many excavations going on at the same time. So we can do this by saying that analysis is performed by the number of excavations. So here we see 13, let's say. So when you execute this, let's see, simulation run, we see that we get 13 excavations running. All of them are with the same specified behaviors as here. And by default here, we see that they are as this, right? So if we will remove them from here, we can add to be here also. And also we see that properties are validated. We see that this one production is not satisfied yet. This is satisfied yet. This is a whole year production, whole year waste. Why we see those red and green colors? Because those properties have those requirements which they satisfy, and we see that they are introducing constraints. So produced more than 3 and wasted less than 110,000 tons. In order that requirement would be automatically parsed, we need to use this project options project general term glossary, which analyzes patterns of the text and converts to constraints. So we can see immediately from requirement what is not satisfied based on that constraint, which is generated runtime. So if we change here, so for example, 0 to 5 or 0, 3, 2, you'll see that the constraint is different, 0, 3, 2, and then requirement here is also shown that it's with some, let's run again. Now we see requirement 0.32 million tons a year. So now how to identify those two configurations, that this excavation is done as this and this one is done as to be. So when you execute the model simulation run, you can remove current excavations which are as is, and here you can configure whatever you want to use from the choices of generalization. Now right click here, add values, and you can add to be, because there is 13 multiplicity here. This is multiplicity 13. You see, we get 13 to be excavators used. And then we can save it as an instance. So we can save this configuration as an instance, and later this configuration can be used for simulation, so we don't need to configure every time. So this includes properties, initial properties, and the choices in the structure of the model. So here, let's see, we already have two configurations with initial properties. And if I will show the column excavations, you see that those are like parts used as is and to be from 1 to 13. Just like a few of them are not visible here, but if I will go here, think here you see the up to 13. Here we have 12, and then this one is 0. So okay, so now the time is to execute this model. And for that, actually, we created another project. You see that this project has shared packages. We can see that we did that by share package. So the reason for that is that simulation analysis project would not update the data here, that it would not actually modify in any way. So we will use this project in another project as read-only. So now I'm switching to that another project here. And actually before that, let me save those changes. So for example, this requirement change, I will switch to my new project. And this project is using this system project. So I will refresh project usages, reload in order to see updated information. So let's check that. So everything got updated. Let's see that requirement is updated. Here you go. So now what we see in this project, so we see that this is read-only. We can perform this usage from here, use project, use local project. And we see here the same model, and we see those packages as read-only, but there are also two new packages. So this one, simulation configuration. So here we specified what we are running in simulation configuration diagram. We specified that we are running as is and to be. We see those configurations available here as is to be. We see also that results will go to the different packages, results location as is and to be. And then instance table which will track those results. Will track those results and will show with the time slot when that result was generated. So this is automatic capability to, if you specify package on result location, so instance will go there automatically from the executed structure, and it will be automatically created, and you can see this in here in this table just visualized. So first of all, what we will do, we will go to the simulation configuration. We will say, okay, run it with the animation, run it slowly, at least a little bit slower, in order to see how that simulation runs, in order not to make mistakes on the whole behavior and logic of simulation before doing any more serious analysis. So let's run as this process. And we see that there is some delays. It takes some time. So those properties were generated, randomized, and we go here, 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 and now the rest of that is till end of the month, 2 months. And we see the time is ticking here. So we can see that actually the whole cycle takes 60 days. Based on this time clock, we see that the time step is 1 day, right? So it is increasing by 1 day because that's the most granular time that we have here, which we want to track, and then it increases our um, clock based on that granularity. We specify this duration properties in the simulation configuration. So here we see it ended. So we'll repeat the cycle. So the cycle is repeated because of this activity diagram. So every iteration it calls again and again this excavation sequence diagram. And could be complicated process here for the excavation. Doesn't really matter. We just call it and track the properties. So it works. Now we can stop it. And we see there is some complaints that that result failed and so on, and this is because we have requirements failing, not satisfying properties, and that's okay. So we just get information that it's not yet satisfying the production amount we will use it for the later analysis. Now we see that I stop it, and then I got the results here with the timestamp as an instance, and also I see this requirement is not satisfied, requirement is not satisfied. The reason here why it's not satisfied is because there is requirement which is not met, but also there is problem that I stopped the simulation in the middle, so not whole year passed. So it kind of okay that they are not satisfied, not all of them satisfied. I will delete this. And now I will run this simulation with updated results, with silent mode. So silent mode will run this analysis as fast as it can. So we'll see that actually the days will tick quickly, will not need to wait for so long. But what we will not see animation. Okay, so let's run as this, and then let's run to be. So as this. So here we see that days are quickly increasing. And actually, I forgot that I didn't specify the duration. So let's come here. Now let's run with the silent mode and also almost no delay for the step. And then what we will not see animation. So let's run it. So you see the days are going, and we see that this is randomized, right? So every cycle, we see that each excavation has different properties, different random duration, different duration for the plant, different for the deviation, and each excavation has its own cycle as this sequence diagram. So all those 13 are performed simultaneously, and they are affecting this total duration deviation and total produced mass and total duration conformance to plan. So done. Now when you say click stop simulation, we will get results here into this instance. So we will come here. So I see here is results, and maybe those old ones they are not needed because again it was not full cycle, so it is not complete year. But this one is complete year, so we see that waste is actually more than expected. The production is still okay based on the requirement, but waste is more than expected. Okay, now let's run this again as is. Let's run as is. I see it's running. Why I'm doing this again? Because I want to compare. Maybe there will be like very different results. So I want to be sure that it will be at a stable level. Again, 1 year cycle, 6 times each excavation and 13 excavations at the same time. So here we see one excavation, here is another excavation, that's the last, and then 366 days took to finish this. So let's stop it. And we got result very similar, same requirement is failing. Now let's run to be. We see it's running fast. Let's stop it again. And in case of to be, so because deviation is always 1 day, so we will see the stable 78, and this one is also stable. So we see 78 days of wasted digging across all the excavation sites. And then production is 78 multiplied by 100 tons per day, we get this one. So if we will run again to be, we will see the same result because it has no difference in the, so we see to be here, it has no difference in duration deviation, so always 1 day. So it's kind of improved process, and we see how much it is improved. It's improved almost, it's improved significantly here, we see. So 100 tons more, 120 tons more excavated per year, 120,000 tons excavated more per year, because this was in million of tons. Okay, so one more thing is that here in this analysis total, here you see this analysis, it takes the each excavation duration, it takes each excavation duration with deviation and on plan, and converts that to the produced material and wasted material, and also it calculates the total duration on plan and total deviated duration. So it actually takes this duration conformance to plan and calculates total duration conformance to plan, takes this duration deviation, converts to the total deviation across all the excavations, and then multiplies those by tons per day and converts to the produced and wasted material. So how that is done with the parametric diagram, which is created inside of this analysis block. Here you see this parametric diagram. So here we take from each excavation duration conformance to plan and duration deviation. We input to this expression, which converts to the total duration conformance to plan and total duration deviation. And then we take this duration deviation total and conformance to plan total, and calculate with those two equations produced and wasted. So deviation is wasted, conformance to plan is produced. We take total rate, multiply by duration conformance, and then divide by a million tons. So all those expressions are created using this expression wizard. You can select this one and invoke this expression wizard. So this is completely transparent. You can add new properties and calculate new values. Here is one trick. You can see that this coming property from the excavation is used in 13, those two properties used in 13 excavations. So we need to put this multiplicity on parameter. Here you see multiplicity is star in order to be automatically summing from multiple values. If you will not put multiplicity here, it means 1. It will not take multiple values coming from different excavations. So this takes automatically for all those 13 and inputs into this expression, which sums and gets the total at any moment in the simulation. So if I will run this to be, we can see how that works. So here I was executing. If I will expand, so you see that duration conformance to plan goes, and total duration conformance to plan is calculated from all those different excavation sites. Here we see automatically calculated based on this expression. So let's wait. Let's see how this will finish. It should be the same to be as it was for this previous one. Okay, done, finish. It's jumping here in order to say that it can't modify this project, which is used as read-only, and we don't want that any modifications would be done, so we can just take a look at those errors on the failed to update the model, but we are okay with that. So we have here results, so the same results. So that demonstrated process as is and to be optimization simulation, and we can for sure change the properties and track different kind of situations, more complicated process, and this is like pattern how to do this, and with sequence diagram. That's what was the main case here, that sequence diagram was used to model process scenario.